will just share my screen. Is my screen visible?
Yes, sir.
Yes, sir.
Right?
Yes,
Okay.
sir.
And the link for today's session is this. I'm just pasting it in chat. Once after the session got over, I will just or just give me one. Okay.
So
Am I audible?
you're not audible from the last 2 minutes. So I believe you
Okay.
missed what
Maybe
we were
now?
saying. Yeah, now you're audible.
Okay, okay. So I didn't said anything. My system got suddenly hanged and I am back now. Mm,
And that's why people are leaving thinking that I think that there's problem with their network.
okay, okay. So I just see my Google Chrome is creating some issue. I will just force quit and I will just rejoin again. Okay. Maybe the session might end because okay. Let's see if it got ended. I will just start right away. Hello.
Yes, sir, you're audible. You're audible.
Am I audible?
Yes, sir, you are
Yes.
audible.
Okay. Okay.
Yes, sir.
So there was some issue suddenly happened. Okay, let's continue where we stopped yesterday. So yesterday we were discussing that problem, and even then at the end of the session also we didn't get a complete clarity on how to solve that problem. I will just go back to that problem at the end of the session, but let's continue with 5.2 and let's finish revising the contents of week 5, and then I will just come back and I will just give you some other way how to think about that particular problem. So the problem I am mentioning is that 5.1 lecture.
Sir, excuse me, sir.
Hmm.
Sir, I just wanted to point out one thing that the Solve with Us sessions is not uploaded after week 2. Can you just upload it?
Solve with a session what?
The Solve with Us instructor sessions, no peer deck ones. Those are not uploaded in our portal after week 2.
Peer deck slides you are
Yeah, yeah.
saying, or the sessions?
No, the slides actually. Yeah.
Slides. Okay, okay. I will check on that. Many students has complained, and even I told them to upload it. So let me check on that, and I will just
Yeah.
upload it. Okay.
What
Actually, sir, the
happens is
sessions are also not available in portal. It is available in the YouTube link, but if we want to see it through the portal, we cannot. It is uploaded only till week 2. The
Okay,
live
okay. I will I
sessions.
will I will check on that. I will check.
and sir, one more thing is that in the calendar, previously we used to have no in the sessions that, for example, open session week 2.
Mm-hmm.
These things are not like now written specifically like which week is to be conducted now. If I like go back into the sessions, then I
Mm-hmm.
don't know which week is this. I need to click to the link and all that. That's just
Oh,
simple
okay,
things
okay,
only.
okay, okay.
Previously, it used
Acha.
to mention in the
Okay,
calendar.
okay, okay, okay. See, this time maybe one of our instructor has created this and he just duplicated it.
Okay, okay.
So when we thought to duplicate it, if we kept like session like week 1, and if we duplicate it every week, it will show as week 1 only. Right? So maybe
Okay,
that's
okay.
the issue. In YouTube, when we stream, we are just differentiating it by having some space week 1, space week 2. But yeah, that's a valid point to note. Yeah.
Thank
So
you.
maybe in next weeks we will just try to update the names.
Yeah, those are very helpful when we try to check through the calendars.
Yeah. Agreed.
Okay. Thank you, sir.
Yeah, thanks. So today is March 1, and so we'll continue week 5, and we will try to analyze, solve few problems, and
No,
try
actually,
to.
how much have you covered? I just joined now.
I just covered only week 5.1, I hope.
Okay.
That too yesterday. Yeah, we just covered like first half an hour. We just did quiz. Two
No,
hours.
not yesterday, sir. Only today. Yesterday,
No. Today I didn't start yet. I'm just
Okay.
starting now. Okay.
Okay, sir.
Okay. So let's start. Yesterday, what we discussed is we are just slowly converting from discrete world to continuous world. So yesterday, whatever we did is we just looked at the continuous random variable and the function of a continuous random variable and how to find CDFs or PDFs or the distribution of functions of a continuous random variable. And then we have seen if that function is one-to-one, like monotonic and differentiable function, then we directly have a theorem and we can use that theorem and directly get the PDF. Okay, so that is what we did yesterday. And then from continuing that, as it is a random variable, so continuous random variable is also a random variable. Once it is a random variable, it will have some expectation, it will have some variance, we can see. So there will be moments, everything. Once it is a random variable, we can analyze, find the central tendency, which is mean, which is also called as expectation, and we can find the spread, which is the variance, like this. So let's look at how to find the expectation in continuous random, expectation of a continuous random variable. So recall that if it is a discrete random variable, so expectation, we did it like, so expectation of a, so this is recall, so expectation of a discrete random variable. So let's say x is a discrete random variable and it takes values from 0, 1 to n minus 1. And the probabilities are, let's say p1, p2. Let's start from 1, 2 to n. And the probabilities are p1, p2 till pn, such that this p1 plus p2 to pn plus pn is 1. So that is how a distribution, a discrete random variable is there. So the expectation of this discrete random variable is expectation of x. What we did the summation of I running from 1 to n. So we took each and every possible value that x can take, and we took that multiplied by probability that that value occurs. I times probability that x takes I. So this is simply summation I running from 1 to n. In these terms, I times pi. So we took each and every possible value, multiplied by corresponding probability, and we just added all those obtained values. And that is what the expected value is in discrete case. But when we come to continuous case, we don't have this kind of structure anymore. So we cannot say x takes values like this, or we cannot count actually. When in continuous case, the values that x can take is uncountable. So you can't count now. And also each and every point if you pick, we don't have probabilities associated to that particular value. We don't have PMF in continuous case. So what we do is, instead of summing, what we do is we do continuous summation. So continuous summation or integration. So fancily we call it as integration. So as of now, I just took, so let's say there is a random variable x which takes values from minus infinite to plus infinite. Okay. So if it is allowed to take from minus infinite to plus infinite, what we do is we integrate it from minus infinite to plus infinite, same x times fx of x. So here this probability that x is equals to I is nothing but the PMF. But in continuous case we have PDF. So instead of PMF we just take PDF and multiply it with that x times fx of x, and we integrate it from minus infinite to plus infinite. So it is not always true that always you have to take from minus infinite to plus infinite. The correct way to write is maybe you just have to integrate it along support of x. So why? Because outside of the support, this fx of x will become 0, right? So what is support of x? Anyone?
Range.
For which the density is greater than 0.
So
Is the range of possible values.
it's like we no longer call it as range. So we say all x such that my density is greater than 0. Okay. So if it is not in the support, that means my fx of x is 0. So you no need to worry about the values which are not in the support. You no need to integrate it again. So the value will be 0 anyway. So the correct way to integrate is you just have to integrate along the support of x. So that will give us the expectation of the continuous random variable. So this just on the same lines, discrete lines only. Instead of PMF, we have PDF now. Instead of summation, we have continuous summation, which is integration. Okay, and representations of these expectations are, maybe we will represent mu x, which represents the expected value of a random variable x, or simply we can represent that mu. So if you know the context in which you are speaking, you no need to represent it with x also. Or we simply say, just like in discrete case, we used to say E of x. You can also represent it that way. And also sometimes we just simply call mean of a continuous random variable. So even if you use mean, the same thing. Okay. So that is about expectation. So we will do problems, but let me complete this variance part also. And the expectation of function of a continuous random variable also. Then we collectively do the problems. Okay.
Sir, support of x means domain of x, right?
Support of x means not the domain of x. Support of x is basically, see, if my x is a random variable, I have PDF associated to it, right?
Yes, sir.
So I will have some PDF, let's say some x in some interval this, and x square in some interval b to c, and 0 otherwise. So you see, if my a, b, c are greater than 0, so you see here, in which cases my fx of x takes values greater than 0.
A to C.
A to C. So the support of x is basically A to C.
Sir, how A to C?
Because within AB, as I said, A and B are greater than 0, it has some positive density here. Even in B to C case also, it has some positive density.
Okay, sir. Yeah.
We just
A to C.
need all x such that my density is greater than 0. Okay, I am working on this x, not on this. Okay. Okay.
Yes, sir. Clear.
Yeah. So yeah, again, variance of a continuous random variable is denoted as variance of x, or sigma square subscript x, or simply sigma square. And here, variance of x, you can write it as we know, right? So usually variance of x is expectation of x minus expectation of x whole square. Right? If you expand this, we will get this. So it is nothing but expectation of x square minus expectation of x whole square. Now you might wonder, I know how to compute expectation of x, but how will I compute expectation of x square? So expectation of x square, so you see x square is a function of x. So x square is a function of x. So if I know how to compute the expectation of function of a continuous random variable, then I can compute variance also. Okay. And for now, believe me that we can actually compute expectation of function of a continuous random variable using expectation of a continuous random variable. Okay, believe me, and we can find this. Okay, if we can find this, then we can find variance of x also. Okay, the same formula, just like what we had in discrete case, that is what we have in continuous case also, but the computation will be different. So computing expectation of x and expectation of x square will no longer have summations and everything. We will have integrations. So yeah, there are some common distributions and their expectations, variance and support. So usually if I say x is uniform from a to b, between a to b, the expectation of x is a plus b by 2, variance of x is b minus a whole square by 12, and proving this is a good thing. You can try proving this using this. So use this formula. You know, if it is uniform, fx of x is 1, and you just have to integrate along the support a to b. It's like, I'll just write it. Expectation of x will be integral. So as we discussed, it is enough to integrate along a to b, which is the support of x, and x times fx of x dx. I know if it is uniform, fx of x is 1. So this I will write 1. So it's like integrating x dx. What am I getting? Okay. So this is 1 by b minus a, right?
Excuse me, sir.
Mm-hmm.
So, the only difference is this, that support will change in x square or whole square.
Which one will change?
Like there is expectation of x square.
Right,
So
right,
only
right.
difference is this, now that the support will change.
Support
Rest
will
of the
change, so the
thing will
integral
be
limits will change.
what, sir?
The integral limits will change if you are
Yeah, only
directly
limits.
on.
Yeah, only limits.
Or else we have one good formula using just the PDF of the continuous random variable. We can find expectation of function of a continuous random variables also. We will discuss that.
Okay.
So before that, if it is uniform, what is fx of x?
One by B minus A.
1 by b minus a. Thanks, at least one. Oh, everyone lost or what?
Sir, b
So,
minus a plus 1.
Why
no,
plus
1
1?
by b minus a is the PDF.
No, that plus one is only for discrete case.
Discrete case. So we
Okay.
are in continuous case. So 1 by b minus a is the PDF. Here also we are using the PDF only. So this is PDF only.
Okay.
Okay. So here it will be, instead of fx of x, it will be 1 by b minus a. So now it is x square by b minus a. We have b x square by 2, right? If I integrate x square by 2, right? Integration of x square x dx is x square by 2. And the limits are b and a. So I will have b square minus a square divided by 2 times b minus a. So this b square minus a square, I can write it as b minus a into a plus b. B minus a and b minus a will get cancelled, and we will be having a plus b by 2. Okay. Even we can do for exponential also. Exponential we have lambda times. So just we need fx of x. The PDF we need. So lambda times e power minus lambda x when x is greater than 0, and it is 0 otherwise. So we don't need to worry 0 cases. We just have to integrate it from 0 to infinite. So the support is from 0 to infinite, x times lambda into e power minus lambda x dx. So if we know some UV formulas, integral UV formulas, we can do this. Okay, so you just bring lambda outside. Okay, you use integral UV, u integral v minus integral du integral v dx. So if we use that, we will eventually reach this 1 by lambda. What I suggest is, please try, if those who know the integrations, those who don't know the integrations, it's okay. Just you need to learn this integral UV formula. So if I have two functions, product of two functions, how will I integrate? So this we studied in Max 1. So just recall the concepts of Max 1. And you can try. See, trying these things is a like it will help you or motivate you to learn more. So we have this, and for normal also, so normal is pretty nice case to observe. If x is normal mu sigma square, that particular parameters which we have mu and sigma square will be my expectation and variance, and the support will be from set of all reals. It can take from minus infinite to plus infinite. Okay, so these are some common distributions, expectations, variances, and support. And let's see the expectation of function of a continuous random variable also.
Sir, one question, sir.
Hmm.
So, sir, for this EX square, do we need to integrate from A to B, or will that range change?
Which one?
For
For
so
what?
for the first one, right? For uniform variance, right? We need to calculate EX square.
EX square, right?
Yeah. So in that case, do we need to integrate from A to B, or will that range change?
Just give me 5 more minutes. I will just come back to this, okay?
All right, sir.
Because if we know how we can compute expectation of x square, then it will be easier. That means if we know how to compute this expectation of function of a continuous random variable, then we can compute expectation of x square. Okay.
All right, sir.
So I should have put this above and that below, but it was okay. Anyway, it happened like this.
Sir, in that exponential thing, what will be the limits to integrate?
The exponential distribution thing, the limits are from 0 to infinite, right?
Okay.
Because I only have my density function when x is greater than 0. So that means my support is x greater than 0. So I have to integrate it from 0 to infinite, x lambda. So x into the PDF function.
Yeah, that's okay, sir.
So let's see how we can compute the expectation of function of a continuous random variable now. So,
sir, what is the limit for normal distribution, sir?
What is the
limit for normal distribution?
Minus infinite to plus infinite, but it will be pretty hard to integrate, because the normal distribution density function will be 1 by root 2 pi sigma e power minus x minus mu whole square by 2 sigma square. Am I correct?
Yes, sir.
X minus mu sigma square. Yeah. So this will be inside your integrals, okay, and it is multiplied by x now.
Sir, again that will be done by integration by parts.
Integration by parts you can do. Yeah, that you can do.
Okay.
If you know that you can do, and you will eventually what you observe is this will turn out to be equal to mu. Okay, this is what expectation is, and we know that the expectation of normal mu comma sigma square is mu. So even people who are interested in this fancy integrations, you can also try this normal also, because anyway this is independent of x. You can bring it outside, and this is also constant. It's like some x square, e to the power minus x square. If you know how to integrate e to the power of minus x square, then it will be easy. But computing e to the power minus x square takes some time. So you have to change the variables. You have to treat x square as some t. Then you will get. Okay, change of variable we have to do, and then we have to integrate. There will be some 2 to 3 steps. which will involve the people who are very much interested. You can try it out. If not, nothing will change. Okay, nothing will change in your life. It's not nothing will change. There will not be any shaky things happening. So it will go as it is. Your life will be normal even if you don't do this. If you do this, you might get excited. Okay, let's continue with this. Expectation of function of a continuous random variable. For that, we need to have some setup. Basic setup is like I need to have a random variable which is CRV. What is the CRV? Continuous random variable. So let's say X is a continuous random variable with PDF. I know fx. Okay, so this I know. So this is the setup I have, and I also have a function g, which is from R to R, and then function of x. Okay, so this is g is a function of x, Okay, then if I want to compute expectation of g of x, what you have to do is instead of x, okay, instead of x, you just have to replace it with g of x, and this will work. And see, this thing plays a very vital role whenever the above integral exists. Okay, so if it is going, if you are not able to integrate along minus infinite to 0, or sometimes it might happen there will be some mods coming into the picture inside this, and you don't need to integrate from minus infinite to 0. Okay, so there will be some cases, few cases, mostly in stats 2 we will not encounter that, but if you do some complex problems, you might encounter few cases where your integral and limits of the integral will play a vital role. But as far as our course concerned, this doesn't play much factor. Limits doesn't play much factor. But what you have to observe is the support of x, which you are using, should sometimes alter, and we will see when will it alter. Most of the times it will not alter. So whatever the support of x is there, that will be the support of g of x also, usually, because our g of x will be either translation or scaling or affine. So it will be like this only. We are not, maybe exponential. Okay, we are not going beyond these things. Okay, maybe a polynomial. Okay, x square or x cube or x. So all these things, the limits will not affect. But if we, as I said, mod or sines, some fancy product functions, which will reduce or which will restrict the domains, basically. So in mathematical words, if I talk, whatever affects the domain of g of x for the values of x, then it will be a problem for limits. But as of now, you don't worry. Do not worry about this. Okay. So main thing is, what you have to understand is expectation of g of x. If I wanted to compute the expectation of function of a continuous random variable, in my right hand side, instead of g of x, we can instead of x times my PDF, I just substitute g of x. Okay. Why is this happening? What we did in discrete case,
So I think g of x can be separated as ax plus b. So then
g of x can be
constant,
separated as,
I mean, in most general case, ax plus b or something like that. And then
no,
they
no,
can
no.
be separated.
In the discrete case, we found that we don't need to find the PMF of or the range of values that the g of x can take and then try to find. We can just treat it as a function and then do over the
Yeah.
x range itself.
So did we do this, like instead of x we just took x square there also?
Yes.
Right? Remember, probability that some x is equals to.
Yes, sir. We did a summation there.
Summation there, but what internally what is happening at the right side of summation? So whatever the function we took, we just multiplied that function to the probability.
Yes.
Right, the PMF. So the same thing we are doing in continuous case also. See, continuous case is not a new thing. So always remember that continuous world has developed from discrete world only. So if the range of the set of values that x, the discrete value, the discrete random variable x takes is very large or becoming uncountable, that is what that is what we call it as continuous, and everything comes from discrete world only. So each and every property and everything that comes from there. Instead of summations or these things seeing separately, we look it as a smaller portions. So that means we are going to see as a integrations dx like this. Okay. So now we can compute, let's just go back. Now we can compute expectation of x square. Right. So what will be expectation of x square? For time being, I will write minus infinite to plus infinite. Later we can change the limits. So simply x square fx of dx. Okay. So if I just go above here in a uniform case, let's take the uniform case as I proved it. So for computing variance, I need expectation of x square also. So what will I do? Okay, let me go to the new page. So I want expectation of x square for x being uniform AB. So what I have to do, I have to integrate it from A to B, x square. Again, fx of x is 1 by b minus a, I know, dx. Okay. So what will I get if I integrate? So if I integrate x square, see this 1 by b minus a, I can bring it outside because it is independent of x. And I have to integrate a to b x square dx. So now integration of x square dx is x cube by 3. The limits are b and a. So what we get is b cube minus a cube by 3. Right? What am I missing?
Yes, sir.
Yes, sir.
Right. So this is the thing we are going to get. And if you know the formulas, it's okay. If you don't know, just do this thing we have, right? Long division. People who know long division, max one, just recall. We know that b minus a, anyway b minus a will be a factor. So you just know x cube minus a cube has a root a. X is equals to a is a root for x cube minus a cube. And using x minus a, then we know that x minus a is a factor of x cube minus a cube. So using that, use the long division, and you will get the other factor also. You get the quotient you will get. So that will be b square plus a square plus ab. Correct? I hope this is correct. And this is by 3. So this and this will get cancelled. So we got expectation of x square as b square plus ab plus a square divided by 3. So we also have expectation of x with us previously, a plus b by 2. So for computing variance, I just need to take this by 3 minus a plus b by 2 whole square. So if I do that, b square plus ab plus a square by 3 minus a square plus b square plus 2ab by 4. Okay. So cross multiply 4b square plus 4ab plus 4a square minus 3a square minus 3b square minus 6ab divided by 12. So this We'll cancel out the coefficients. And finally, we are going to have b square minus 2ab plus a square by 12, which is b minus a whole square by 12 or a minus b whole square by 12. Usually we write b minus a whole square by 12 because b is greater than a. So b minus a whole square by 12 is our variance of random variable x when x is a uniform AB. Okay. So again, for computing, so we can also do exponential normal also, but as we don't have enough time, I'm not going to prove, but I suggest you to do this thing. Instead of this x, you have to take x square and integrate it, and you will get expectation of x square, and then you just do expectation of x square minus expectation of x whole square. Okay, so let's do some problems now. So x is a continuous random variable with PDF given like this. Okay, so we are interested to find expectation of x. Yeah, Devansh.
Sir, in the lecture that we saw for the week 5, there sir had also taught about the CDF calculation part. So there we were taking limits while integrating, and we did not take absolute limits like minus pi by 2 to pi by 2. For example, if you see the example of 1 by 2 cos x, so we had to find this CDF of it. So we didn't directly integrate from minus pi by 2 to pi by 2. Instead, we integrated from minus pi by 2 to x. So why is that so? I mean, why are we integrating only till x?
As it is CDF, right? You are trying to find CDF from PDF, right?
Yeah.
So how do we find CDF from PDF? Like, so
I mean,
see, many people might confusing there only. So if
I mean, if you integrate from minus pi by 2 to pi by 2, you'll always get 1 only, no?
One,
because
right?
you're integrating the entire range. So you want to find the PDF, that's why you're taking the upper limit as x.
So
I mean, the
remember,
CDF
always remember this graph, okay? So if you have your PDF with you, if I want fx of x, see x, this small x is not a random variable, it's actually a fixed x, like some x, some any x. Okay. And whatever the area under the curve till x is there, that will be the CDF value.
Okay.
Okay. So in order to get the area under this curve, what you have to do, you have to start from minus infinite, or you have to start from the lower possible value to till x.
Okay, but while notation we write it as minus pi by 2 to pi by 2, like over the entire real values.
No. Always CDF is also a function, okay? It's the function of this x, okay? So you give me an input and it will give you output. It's a function, okay? It's not a constant value. Okay, CDF actually gives you the probabilities till that value x, and that x is my input. So I don't know what x is, but it's an input, constant input.
Okay.
Okay. So if x is this, the area fx of x value will be this. If x is somewhere here, okay, then you have to integrate. X is this, you have to integrate till here. Okay, it will depend on this x. So if you are confusing with x, you just count like minus 10. Fx of minus 10 is different from fx of 10. Right? If you just take limits from minus pi by 2 to pi by 2 always, then these both will take the same values. Right? It's not always. The upper limit will be x. Okay, so how shall we do this? Like, what's the approach? Shall we directly?
We can break it into 1 to 0 and 0 to 1.
Break it into 1 to 0, 0 to 1 because I don't want mod in my integrations. Okay, So let's try by what we know. So what we know is, in order to find the expectation of x, I have to integrate it from support -1 to 1. So I have support from -1 to 1, x times my fx of x dx. And then I know that my fx of dx, fx of x is 1 minus mod x dx. So now you see, integrating mod x is bit painful. Okay, and we can remove mod easily. So I can remove mod easily. How can I remove mod x? I know the function mod x. So it will take x if x is greater than 0, or it will take minus x when x is less than 0. Right? So that is what we are going to do. So when x is in between, when x taking negative values, so negative values means here in our support, from -1 to 0 is my negative values. So what I can do is, from -1 to 0, I can split the integral. -1 to 0 x times 1 minus. Now my x takes values between -1 to 0. I know that instead of mod x, I can simply write minus x dx plus, from 0 to 1, my x is positive now. If my x is positive, mod x will simply take x. So I can write x times 1 minus, simply instead of mod x, I will just simply write x dx. Okay, so that is how I can compute. So now it's like x
Sir,
plus x square. Yeah.
interrupt.
Sorry, mod x means we should remove the sign, right? Is it not like that?
Mod x is like, mod x always takes positive values. Okay, so mod x is the mod function.
Correct.
So this is what mod function is.
Yeah. So when we say mod x, when it is -1 to 0, then we should remove the minus, right?
So that is how we remove the minus, right? When x is taking negative values, so that means minus 0.5. If my x is minus 0.5, what will be my mod x?
X 0.5
plus 0.5, right?
So, but here you have mentioned inside the bracket -x, right?
Yeah, plus 0.5. How will I get plus 0.5 using x? So if I minus of minus 0.5, so minus of minus 0.5 is plus 0.5, right? Agreed?
Okay.
So minus x. So mod x will take minus x when x is negative. So if x is negative, in order to make it positive, what should I do? I should product it with minus, right?
Right. Okay.
So that is mod function.
Yes.
So now you see, any value, this will be positive. So x, if x is positive, x is positive. If x is negative, minus of x is positive. So that is what mod x is. Okay. Yeah, so that is how we split it. We split the intervals into negative interval and the positive interval. In the negative interval, instead of mod x, I just used minus x. In the positive interval, instead of mod x, we used x. And we can integrate. And x minus x square dx. Okay, so now we got some, it's just the polynomial. You can just integrate it. So x square by 2 plus x cube by 3. And the limits are 0 minus 1 plus x square by 2 minus x cube by 3. Limits are from 1 to 0.
Sir, I'm getting 0. Is it completely wrong?
See, sometimes you will take plus, minus, you will get confused. Okay. So, maybe let's try to solve this and let's see what might had happened if it is 0. Okay, let's compute it. I hope. Okay, if it is 0, it will be 0. Right? Agreed?
Yes, sir.
Yes. Okay.
And the next part is minus of -1 whole square by 2 plus -1 whole square by 3. Okay, this is 0.
Whole cube.
Whole cube, sir.
Yeah, okay, whole cube, correct. And plus, so for the 1, it is like 1 square by 2 minus 1 by 3 minus, and the 0 is 0.
Yes, sir.
Now this will be like minus half plus 1 by 3, right? So there is a minus.
Yes, sir. Then plus half minus 1 by 3. So 0.
Yeah, plus half and minus 1 by 3. So we are getting 0. So expected value of this function is 0. So what it says that it's actually, see, expectation of x can be 0, right? So if I draw the graph of this, how will it look? Maybe that will give much more clarity why this became 0. So if I just try to draw the graph of this density function, what will I have? I will have straight lines only. So when x, so you just see here also you can just remove mod. If I remove mod, what happens? My fx of x will be 1 minus of minus x when x is in 0, and 1 minus of x when x is 1, and 0 otherwise. So this is like 1 plus x, and this is 1 minus x. So 1 plus x is a straight line, and 1 minus x is also a straight line. So they will be like this, I guess. So 1 plus x will be like this. 1 minus x will be like this. Okay. So yeah. So area under this curve should be equal to 1 because that is a density function. You can check this will be minus 1, 0. This is 1, 0. And this is 0, 1. Okay. So the area will be 1. But you see now from the graph, what you observe, at 0 it has high density, and also it is symmetric around 0.
Yes, sir.
Observe that. So it is symmetric around 0, and also the high chance, my random variable, it has high density at 0. So if I compute the expectation, my intuition says that my expectation should also be at 0. So my expected value of this continuous random variable will be 0 because it is symmetric around 0. Okay.
Okay, sir.
So half the probability will be the left side of 0, and half the probability will be right side of 0. So that is where mean lie, right? So how many of you observe this point? Probability that x greater than mu, where mu is mean, will be equals to probability that x less than mu if it is symmetric.
Sir, can you please illustrate the calculation of CDF for the same case?
For this, is it? We will try to find the CDF, is it?
Yes, sir.
Okay, let's try that thing also. So now I will bring that graph down. So this graph will help us maybe for computing CDF. So let's try to find the CDF of this thing. Okay, I want this fx of x, I want, and this is nothing but I have to integrate from, so minus, so the lower limit, which is minus 1 to x fx of x dx. Okay, so that means in the graph, if you see, if my x lies in between minus 1 to 0, so somewhere x, I just say somewhere x, this x, I just have to simply integrate from minus 1 to x with this line. But if my x, so see, if this is, I can simply integrate minus 1 to x, and my fx I just simply write as my fx is, this is 1 minus 1 plus x, and this is 1 minus x. So I can instead of fx of x, I can simply write 1 plus x dx if my x, whatever the x is there, is in between minus 1 to 0. Okay, so this x can vary from -1 to 0. Even though if it is varied from -1 to 0, my fx of x is 1 plus x. So I can compute like this. So if I integrate it, I will get x plus x square by 2, and the limits are x and -1. The x plus x square by 2 -1 minus -1 whole square by 2. No. So that is why sometimes it will happen like that. Minus of, I will take -1 plus -1 whole square by 2. Okay. So this will give me x plus x square by 2 plus 1 minus half, which will give me half. Okay. This is when the small x is from -1 to 0. So I should also compute for all x. It's not for only -1 to 0. So what happens when x is greater than 0 till 1? So it can take till 1, right? So when my x lies this side, so if my small x is this, I have to compute the area under this curve till here. Okay. So what you can do is, usually you can integrate this part separately and this part. So this part separately and this part separately. If you integrate this part, you will get half. So that is very easy to observe from the graph. So half the probability will be left side of 0 and half the probability will be right side of 0. Or else you just integrate it from -1 to 0. You just take 1 plus x dx. What we are trying to do, I wanted to integrate it from -1 to x, fx of x dx, where my x is now the right side of 0, or where my x is in the interval 0 to 1. So for that, I need to split my interval from -1 to 0 and from 0 to x, because my fx of x is different for these two intervals. So I can integrate it like this. So if I integrate this, I will get half. So you just write out, we will reach half plus, and if I integrate this, I will get x minus x square by 2, and the limits are x and 0. So we are going to get half plus x minus x square by 2, and the 0 will be 0. So now, what I can write is, I will just go back to blue. Fx of x collectively, when x is less than or equals to -1, write the simple things. When x is less than or equals to -1, it is 0. I know that. When x is greater than or equals to 1, it is 1. So this is for sure, right? The other parts are, I have two intervals now, where the intervals are from -1 to 0 and 0 to 1. I'll use this maybe. This will be better. Okay. So what we got in the first case, from -1 to 0, we just got x plus x square by 2 plus half. And in the second case, what we got? We got half plus x minus x square by 2. So if you check, this will be a continuous CDF. So the only points you have to check is -1, 0, 1. So that is where the continuity might disturb. So if you check, you will get at all the 3 points, the graph is continuous, the function is continuous. You just have to check the left hand limit and the right
So
hand
only
limit.
derivative will not exist, right? Because this is a mod function.
Sir, can you just scroll up a bit?
Scroll up, is it?
Okay, sir. Done.
Okay. Okay. So this is the CDF. This is how you can compute the CDF. But observe one thing. In order to compute CDF, the limits are from -1, always start from the lower limit of the support, lower value of the support, to x. And why we are splitting here, in this case, why we are splitting? Because my fx of x, which I have to integrate, is not the same for both the limits, both the intervals. My fx of x is changing after 0. So I cannot directly integrate. So what I do is I split the integrals. So it is true, right? In order to compute the area under this curve, till here, instead of computing directly, you can compute area under this area of this triangle and then area of this, and add both of the areas. You will get the same area. So that is what we did. So this is area of this. This is area of this. So that's it. Why we split? Because the PDF changes. Okay. So this thing you can do in any case. If your PDF is changing, then try to split the integrals and see the CDF. And you will get. Okay. Let's do one more problem, which involves function of a continuous random variable. Now I have given PDF of x as like this.
Sir, generally, if mod functions are given, then in general, will the PDFs be 0 means after integration? Expected value.
No, right?
Expected value and variance. In general, for mod functions.
No, not in general for mod functions. See, here the limits are, here the graph is symmetric, okay? Even I can have a mod function, but graph may not be symmetric. Just like, okay, I don't want to disturb this. Just like you take 2 minus mod x, and you take limits from -2 to 1. Okay, understood? So what I said is, you just take Control C.
Sir, what I mean is every mod function is symmetric. So then integration will yield 0 ex.
Okay. I don't think it will give. Let's see. It's not 2. So let's take it as a constant because this should satisfy PDF properties. So it has interval 3. So C times, let me keep it 2 only. So you just have to find C such that this becomes a density function. Okay, you understood this thing? But once I draw this graph, it may not give you the expected value to be 0, but it will give you somewhat expected value to be a negative value.
So we have to find C's such that it is not negative, right?
No, we have to find C such that it satisfies this properties. So integral -2 to 1 fx of x dx is 1. So it should satisfy PDF properties, right?
Okay, yeah.
So you can find C, and then what happens is it will not be symmetric. Even though it is mod function, it will not be symmetric around 0. Then if it is not symmetric around 0, this will be symmetric around the mean. Okay, and that mean may not be 0. That mean may be somewhat like this. It might be like this.
Actually, like the old mod function itself, if we do like one affine transformation or the
correct.
translation.
So if we do some translation, yeah, that's better, right? If I just shift this graph to somewhere like this, somewhere to right side, even though it is a mod function, then also it will be a mod function. So like this, to the right side, then also it will be a mod function, but the expected value will not be 0 there.
Okay, for example, if we write x mod x as x plus 1, then it shifts and mean also changes.
Mean also shifts. But one thing you can observe is this mod functions will be symmetric around the mean, where mean is not equal to 0. May or may not be equal to 0, but it will be symmetric around the mean.
Understood, sir.
Okay. Yeah.
So using symmetry, we can find means.
Yeah, the axis of
Uh-huh.
symmetry gives the mean, right?
Uh-huh. Yeah. So let's do this. This is an activity question, I guess. The PDF is given to us. PDF of x is given to us. We need to find the expected value of x square. So pretty straightforward only, but let's try to get used to this finding expectations of functions of a continuous random variable. Okay, so I recommend everyone to try this, try it out. Once we solve this, we can move to the last lecture we have.
So in case of x square, will only multiply it by x square or will change the function too? Like we'll make it x cube in 0 to 1 interval. Or we just multiply it by x square in the place of x as the
See,
formula.
we just have to, yeah, you just have to use the formula. So that is what, instead of x,
Okay,
you
we'll
just take x square.
Okay,
That's it.
only that thing.
Yeah.
Okay.
So as we have expectation of x, so you just have to use this expectation of g of x is integral. So wherever the support is there, g of x, now you have to take in place of x, you have to take g of x times fx of x dx. That's it. Okay.
So it's
So those-
1.16.
Okay, those who are I just want it in fractions. I don't want. Any answers? Any options?
1.16.
I just want it in fraction. If you can able to tell me in fraction.
Fraction means, sir?
Like a by b.
Okay, okay, sir.
29 by 25.
29 by 20.
5.
My,
25.
29 by 25 is my first option. So let's see who else.
1 by 12.
1 by 12 is my second option.
Sir, 14 by 12.
40 by 12.
14 by 12.
14 by 12. It's like 7 by 6.
Yes, sir.
Further simple. Yeah. Okay, my option C is 7 by 6. I'll just wait for one more option.
Minus 3 by 2.
Minus 3 by 2.
No, I don't know why I'm getting a minus.
Okay. So without computing, just tell me what will be the range of my expected value of x square? What could be my range?
0 to 2.
Or what could be my support of x square?
0 to 4.
0 to 4. That's a good guess. If you want to guess, you should guess between 0 to 4. Right? If you are running out of time, and this will happen always, then if you wanted to randomly guess, it will not be 0. It will not be 4 also. Okay. So you can remove the boundary points. Maybe 0 to 4, somewhere 2 or 1. So nearer to 2 or 1 is a good guess. Like better guess. Okay, no option D is it? Okay,
I'm getting minus 7 by 6 actually.
Okay, minus 7 by 6. So let's give that option. Okay, let's try to solve. So let's try to solve step by step. Okay. So I want expectation of x square now. So what I have to do? I have to do x square into fx of x dx, and the limits are from minus infinite to infinite, but I don't need minus infinite to infinite. I just need simply from 0 to 2. Right? And now you see from 0 to 2. Can I? Narendran, can you please mute, because
Narendran, please mute.
Yeah. So now you see I can't integrate directly from 0 to 2 because my fx of x changes. In some interval it is x, and in some other interval it is 2 minus x. So we can split the interval. We can split the integral. What we will do is we will split 0 to 2 x square fx of x, 0 to 1 fx of x dx plus 1 to 2 x square fx of dx. Right? So once I split, now I know in the interval 0 to 1, I know fx of x is x. Simple. So 0 to 1 x square x dx plus from 1 to 2, I know fx of x is 2 minus x dx. So this is, if we solve, now we got all the things we want. So this is x cube dx, and we know how to integrate this. And the next expression is integral 1 to 2 2x square minus x cube dx. Even we know how to integrate this. So if I integrate the first thing, it will be x power 4 by 4. So this I am using this, okay. Integral x power n dx is nothing but x power n plus 1 by n plus 1. Okay. X cube will be x power 4 by 4, and the limits are 1 and 0 plus again. So 2 is a constant, so I will write it neatly. This is how integration we do. So 2 is a constant which is independent of x. I will just bring it out, and I can actually split the integral. So I can actually write integral 1 to 2 2x square dx minus integral 1 to 2 x cube. So this is like 2 x square dx minus integral 1 to 2 x cube dx. So now everything use this formula. Now everything you can do. So plus 2 times x cube by 3, and this limits are from 2 to 1, minus again x power 4 by 4, and this limits are from 2 to 1. Okay. So this is like 1 by 4 minus 0, the first term, and this is plus 2 times of, so this 2 is outside, okay. So 2 times of 2 cube by 3 minus 1 cube by 3 minus 2 power 4 by 4 minus 1 power 4 by 4. So this is how we have to substitute the limits. So this is 1 by 4 plus 2 times of 8 by 3 minus 1 by 3. So 7 by 3 minus, this is 2 power 4, which is 16 by 4, which is 4. 4 minus 1 by 4, it's again 15 by 4. Okay. Till now it's okay. Now we got all the numbers. So basic arithmetic simplification. So this is 1 plus 14 by 3 minus 15 by 4. So this will again be like 1 by 4 minus 15 by 4. It is 14 by 4. 14 by 3. 14 by 4 is 7 by 2. Right. If I simplify this now, I am going to get 28 minus 21 by 6, which is 7 by 6.
Yes, sir, we got the answer.
Okay.
Yes, sir.
So the answer will be 7 by 6.
Sir, 1 minute. Means I solved it and 7 by 6's answer. You in between referred to this from 0 to 4 is a good guess. What was it? I didn't catch that.
0 to?
From 0 to 4 between the answer should be
guessing thing. Okay.
Yeah.
So my x random variable x takes values from 0 to 2. And where will my x square take? It will take from 0 to 4. if it takes, it will take from 0 to 4, right?
Yes.
And we know that expected value will lie between the lesser value and the greatest possible value.
Oh, okay, understood.
Okay. So
So if we get something outside of that, we should know it is wrong. That is why you told us.
That is how you can check. If you are getting somewhat like this -7/6 as your expected value,
Okay.
X cannot take that value first of all. Okay.
Understood, sir.
All the values that X takes are greater than that value. How can expected value is like central tendency. It's like some half of the values will be left side of the mean and half of the values will be right side of the mean. That is what expected value is, right? Center point.
So, sir, from 0 to 4, the mean is approximately 2. And since X does not involve like 0, beyond 2, it does not involve numbers. So anything between 1 to 2 may be good.
See, this is that is what I said. Anything between 1 to 2 is a good guess, but it may not be correct always. Okay.
Yeah, that is true. Estimation.
Yeah, it's just it's the best way to guess. So guessing also requires some strategies. So it's not guess. See, sometimes you might get correct by guessing also. Okay. So let's move and talk about this Markov's and Chebyshev's again in continuous case now. So just like discrete, nothing changes. Formulas and everything will not change. What changes is the distribution, what we have. Okay. So now we have X as the continuous random variable with mean mu. Again, the support of X should be non-negative, just like what we had in discrete case. So the range should be, the X should take non-negative values. Here also the support should be non-negative. I have this Markov inequality states that probability that X goes very, very far from mu has very, very less chances. We can actually bound it. So I just drew a number line and I just showed you. So if this is mu and this is C, now I no longer have X will take this. I no longer have that. X can take any value continuously. And now it is very easy to see that even if I write probability that X greater than or equal to C or probability that X greater than C, it doesn't change much. So the equality will not play much role in continuous cases. So the probability that X taking values greater than C means in this region as less than mu by C probability. Okay. And also I mentioned that Markov inequality is very, very weak inequality unless C is very, very large. So if C is somewhere nearer to mu or if C is less than mu or C is nearer to mu, this inequality looks rubbish.
In one of the activity question, there is X is less than C, then the equality sign change and the mu by C is 1 subtracted by 1. So how it comes?
So that is all right. If X taking values greater than C is less than mu by C, X takes C. We are just splitting X takes values greater than or equals to C and X takes values less than C. Okay. So what is the probability that? So can I get some relation between these two?
Yes,
probability that X greater than or equals to C and probability that X less than C.
So it will be 1 minus probability of X greater
It
than
will
C.
be 1 minus, it will be complement basically.
Right. So what will it be is the probability that X greater than or equals to C is nothing but 1 minus of probability that X less than C. Okay. So if this is less than or equals to mu by C. Okay. So let me try to give you it's like 2-line proof, but yeah, anyway, yeah. I'll just give you. See, what I have is we have this inequality with us. Probability that X greater than or equals to C is greater than mu by C is what I have. And I know that probability that x greater than or equals
Lesser
to
than mu by c.
yes, sorry, lesser than or equals to mu by c, and I know that probability that x greater than or equals to c plus probability that x less than c is equals to 1. So now probability that how can I write this? Okay, so what I will do is I will subtract 1 from, okay, I will take negative of this. Okay, both sides I will multiply negative. What will happen to the inequality sign?
Will change.
Will
It will reverse.
It will reverse, right? So 1 minus probability of x greater than or equals to c. Okay, not 1 minus probability that x greater than or equals to c is greater than or equals to minus mu by c. Correct? Agreed?
Yes, sir.
So now what I will do is I will just add 1 on both sides. So from here to here, add 1 on both sides. So I am just multiplying minus 1 on both sides. Multiply. Okay. So what will I get? 1 minus probability that x greater than or equals to c is greater than or equals to 1 minus mu by c. Okay. And from here, I know that probability that x less than c is 1 minus probability that x greater than or equals to c. So instead of this, I can simply write this. So from here, what will I get is probability that x less than c is basically greater than or equals to 1 minus mu by c. So pretty easy proofs, easy to intuitively also it is very easy to guess. If my probability that x taking greater than or equals to c is less than mu by c, probability that x takes values less than c will be greater than 1 minus mu by c. So because the probability sum should be equal to 1. So intuitively also you can
and we can also take some examples and see, like, if 1 by 2 is bigger than 1 by 3, but if we subtract from 1 minus 1 by 2 is smaller than 1 minus 1 by 3.
Yeah.
So just taking some examples.
Taking some examples, you will get an idea. If you are not okay with variables like x, c, mu, everything, just take random examples. You just substitute some
Inequality will change.
Inequality will. Okay, from there you can get. Just like again, we will just discuss this Chebyshev's also, and I have one problem, and we will solve it and we'll move.
What if it is less than or equal to? Less than equal to. What will happen then?
That is what, right? In continuous cases, equal to doesn't play much role. Okay.
Okay.
So even if it is x less than c or x less than or equals to c, it doesn't matter in continuous cases. Continuous gives you that liberty.
Okay.
Okay. Yeah.
And discrete only
now
changes.
In discrete only this equality plays some role.
I mean, in this Markov thing, the change.
So yeah, there will be change. So then you have to be like in order to have this, you have to be like x less than c plus probability that x is equals to c.
Okay, so that is
and you can compute this, yeah, and then you can bound it. Okay. Okay, and Chebyshev's also the same inequality we have, but right now we have in front of us the x is actually the continuous random variable instead of discrete. Now it is continuous, and the probability that my x will lie within k standard deviations from mean will be away from mean will be less than or equals to 1 by k square. So the same formula. So the other formula is mod x minus mu, again less than or equals to k sigma will be greater than or equals to 1 minus 1 by k square. So the other thing, that means within the standard deviations, the probability that x lies within k standard deviations from mean is greater than or equals to 1 minus k square. So there is a high probability that my random variable x will lie very nearer to mu, is what this Chebyshev says, and Markov also says the same thing. So whatever the x that values takes, that will be very nearer to mu. Values that x takes very far from mu has very less probability. Okay, let's try to solve this problem. So this is also, I guess, it's an activity question, but I change this 3 standard deviations now. So x is a continuous random variable. Now what I want is, I want you to bound the probability. So I didn't mention you that whether it is upper bound or lower bound. I just want you to bound the probability that x takes values within 3 standard deviations of the expected value. What this means? X takes values within 3 standard deviations of expected value. So I have x
Standard
means
deviation
maximum.
Yeah.
3x.
It's a
Maximum
minus
probability.
Lower bound.
0.88.
8/9.
Right? 0.88. 1 minus 1 by 3 square.
8/9.
No. I just want, what is this x takes values within 3 standard deviations of expected value?
X
So
minus
what will be this?
X minus mu less than equal to k sigma should be
So here
greater
k
than
would
1
be
minus 1 by k square.
1 minus 1/9. 8/9.
So this is what it means. So
Yes,
this line means x taking values within 3 standard deviations of the expected value means x minus mu will be between minus 3 sigma and plus 3 sigma. Okay, and we asked you to bound this probability. So how can I write this probability? This probability I can write mod x minus mu less than or equals to, or okay, let's keep equal to. As I said, equal to doesn't play much role in continuous cases. So this is 3 sigma, and using Chebyshev's now, how can I bound this? This will be greater than or equals to, or less than or equals to.
It will be greater than
Greater than or equal to.
Greater than or equals to 1 minus
1 by
1
k
by k square.
1 by k square, and k is
3.
3.
Root 3.
3 here. So 3 square. So this will be 1 minus 1 by 9, and this will be 8 by 9. So what is this? What we got? Probability that mod x minus mu less than or equals to 3 sigma is greater than or equals to 8 by 9. So that means the probability is at least. So this is a lower bound, right? At least 8 by 9. Correct? So the minimum value that this probability can take is 8 by 9, and it can take any value above 8 by 9 also. So that means you can say, collectively you can say at least 8 by 9. So this probability is at least 8 by 9. And you can say the lower bound of this probability is 8 by 9. So this is the lower bound. Okay. So like this. So converting this, see, this is the main problem. Okay. So once you can convert this, you can use formula, you can get whatever you want. But converting this English statements into our mathematical expressions is the key. So practice more on these things. Okay. Okay.
Sir, in the question we were asked to find the probability that it is 3 units away from the standard deviation.
3
like the
standard
x variable.
deviations of the expected value. Yeah.
So expected value is like mu. Like we had to find just for the x, na? But we found for x minus
See,
mu.
this is mu. X is the realization. Okay. X takes values. So this x is values that x takes.
Okay.
So this is the value, and it should be within 3 standard deviations of the expected value. This is expected value, and these are the values that x takes, and the difference should be within 3 standard deviations. That means 3 sigma.
Okay. So if it was like for x takes between 3 standard deviations, then it would have been just x at not minus mu there.
See, standard deviations are computed from mean, right? So first standard deviation will lie 1 standard deviation right side to mu and 1 standard deviation left side to mu.
Okay.
Right? So,
yes, sir.
So pretty hard to interpret that within 3 standard deviations. x takes values. Okay, you can say it like this: x takes values within 3 standard deviations means this is what it means: probability that minus 3 sigma less than x less than 3 sigma. So this is what we are asking.
So I was just confused between these two statements.
No. So what we are asking is within 3 standard deviations of the expected value. So from the expected value, maybe off is not a good word, maybe from the expected value.
So it should be mu minus 3 sigma and mu plus 3 sigma, right? X taking values.
Yeah. So
that's it's
no.
falling between mu minus 3 sigma, mu plus 3 sigma. Basically, if you put the inequality to the other side, that is, if you bring mu to the other side, it will become that statement that's wrote that minus 3 sigma less than equal to x minus mu greater less than.
Right. Okay. See, x takes values within 3 standard deviations is also same as like this, because see. Okay, I will. Here is some space. So this is mu, and this is, let's say, 1 standard deviation, and the next is 2 standard deviations. Okay, so we are asking you, let's take only 2 standard deviations. Okay, let's not go 3. So if I ask you x takes values within this, x taking values within this, what it means, what is this point and what will this point be?
That will be mu minus 2 sigma.
Minus 2 sigma and mu plus 2 sigma.
So this is mu minus 2 sigma, right? Mu, and this is mu minus sigma, and this is mu minus 2 sigma. Here also it is mu plus sigma, mu plus 2 sigma. Okay, so x takes values in this means x is taking values in this interval, means x is lying in between mu minus 2 sigma to mu plus 2 sigma. Okay, that is how you have to think. When x is taking values within 2 standard deviations means x is taking values in the interval mu minus 2 sigma to mu plus 2 sigma. So 0 will be somewhere here. Okay, somewhere here, or it might be here also. It might be right side also. But mu is not 0. Okay, and we are looking around mu only always. X takes values in the interval.
Sir, in normal thing, mu will become 0, no, sir?
In normal thing, mu will become 0.
So it is not shown what distribution. So mu can be anywhere.
Mu can be anywhere. Correct. So yeah, so that is what I said, right? This will be a bit confusing. So that is the main thing you should do. Converting this English statements into our mathematical forms is the main thing. And as you go along the course, this will occur. This problem will occur continuously. Let's say now, right now it is discrete for you. When week 7 starts, this problem will become continuous. Okay, if you don't work right away, so you just have to be like, you just have to be ready what comes next. Okay, so that is about that. And so we have one more lecture in week 5, which is which talks about joint distribution between discrete and continuous. So now we have talked about joint PMF between 2 discretes, and we also studied a lot on continuous random variable. Now what happens when I look at jointly between a discrete and a continuous? So can I get the joint distribution? Can I see the joint distribution actually or not? And if discrete is given to me, for suppose discrete is given to me, can I compute continuous? Or if continuous is given to me, can I compute the PMF for marginal of discrete? And the answer is yes, we can do. If I have given you the joint distribution, or in this case, for our better understanding, we are not going to start from joint. Instead, we start from looking the joint as product of marginal to conditional. So we will understand the conditional distribution. We will understand the marginal distribution of discrete. And if I product this marginal times conditional, I will get joint. This is the prime property we know. So this we know, right? Joint is basically product of marginal into conditional. So instead of looking at joint directly, how we look at joint is we just look at the marginal of discrete. And conditional, how we condition is we condition on continuous given discrete. Okay, so that is how we are going to see the joint of discrete continuous, and from the joint we will try to look the marginal of continuous. Okay, that is the setup now. So xy is jointly distributed. X, let's take x, my first random variable x is a discrete. As it is discrete random variable, it has some range tx and PMF px. So I just change the notation from fx to px, but I hope that's okay. And now we see the conditional distribution of y, the continuous random variable. So how we see is for each x, so I take as it is a discrete. Yeah, any doubt there? Yeah, Amit. Amit, do you have any doubt? If so, you are on mute. You have to unmute yourself and talk. If not, just, yeah, thanks. Okay. So as x is discrete, I have now I have range and I can order my range. And for each x in my range, we have a continuous random variable y, which I denote it as y given subscript x. These are the same notations which professor has used. You just go back to the lectures also, you will see the same notations. So yx with density. So as I said, this yx is a continuous random variable. It has some density. I will denote it as fyx of y. Simply it is saying that this yx is basically y given x is this capital X is equal to small x, and this small x is basically belonging to the range, and this fyxy is the density function, is the conditional density. We call it as conditional density of y given x. So that is how we call. Okay, and denotions.
So here the range of x becomes a support for y.
Range of x becomes
the support for y.
No, it's not support for y.
Y is
for each value of for each x in my range, there is a separate distribution for y. It's like for each x there will be a different support for y, different supports for y. Okay, so what it means is if for example, if x, these are disturbing much, if x takes value 0 1, I will have, so when the small x is 0, I will have y0, which is a random variable, continuous random variable. It will follow some distribution, some continuous distribution, let's say normal, maybe normal some 1, 0.5. Okay, so this y0 is basically conditional distribution of y, given x is equals to 0. So likewise, I will have y1 also, which is conditional. This is also a conditional random variable. Okay, continuous conditional random variable. Maybe this might follow some uniform 0. Okay, so this each and every yx is a continuous random variable, and this x comes from the range of x. So if my discrete random variable takes some 100 values, in my range it has some 100 values, I will have 100 different continuous random variables. And each random variable will have its own support. So here the support is, if it is normal, the support will be all set of all reals. If it is uniform between 0, 1, the support will be 0, 1. If it is something else, the support will be computed according to the how the random variable is behaving. Okay.
Yes, sir.
Now, once this is known and this is known, I can what it means is I know the joint, right? So this is known and that is known. How can I compute the joint? So I want to compute
marginal into conditional.
fxy of y. Simply I will just take marginal. Marginal is nothing but the PMF of x, will be the PMF of x times
fx.
Okay. So this is what it is. And now in order to compute the marginal density of y, okay, now I want to compute the marginal density of y. So marginal density means I wanted to look the distribution of y. So I don't want this subscript x anymore. I want the distribution of y collectively, or maybe independent of x. Okay, separately, marginal. So we did this marginal in discrete case also, if you remember. Did we?
So adding up?
Sir, there we added. Now I think we have to integrate it.
No, why? X is
This is
anyway
PDF,
discrete, right? X is anyway discrete, right?
Yeah, so we'll be adding up like 0 plus.
So what we do is, in order to compute the marginal density of y, we will add sum over all the possible values of x for my joint. So you observe why I have written this. So this is nothing but the joint. So px, so this is marginal of x, and this is conditional density of density, let me call it as density of y given x. Okay, so this is conditional I have, and I am producting it with marginal. So that means collectively I am taking this as joint. This is joint, and if I sum over all the values that in the range of x, I will get the marginal of y. So that is what we did in discrete, right? Here also, as x is discrete, I can do the summation. X is not discrete. Huh?
Why this marginal x is not being written as fx of x? Why it is being written px of x?
See, I just said, right? I just use that notation. If I want to use fx, I can use fx also. Okay. So usually why we denote it with p is because it is probability mass function. So now that we have probability density functions also into the picture, instead of this fx, we just write p. P represents it. It is representing the PMF, probability mass function of a discrete thing, and the small f is like density thing. Okay. Just to differentiate both. If you want to write fx, it's fine. You can write. And let's solve this problem. Now you see, I have given you the distribution of x. So that means I have given you the PMF of x, range of x, everything is given. And also I have given you the conditional density of y given x. So this is like, this is the thing we are discussing. This is yi. So for each I in my range of x, I have my distribution, separate distributions. What I am interested to find is the marginal density of y. This is marginal density of y.
Sir, the probability at a point for a joint distribution also will be 0 here.
The probability
At a point will be 0 here for the joint of discrete and continuous.
at a point it will be 0, right? Okay, so how do we do this? Just plug into the formula we have. So that is what we are going to do. So summation, this I is from 0 to 2. So Px of I times Fy given x is equals to I of y. Right? So as I said, it is uniform. The probabilities will be 1 by 3, 1 by 3 and 1 by 3. So that means this Px of I is same for all the 3 cases. So this will become Px of 0 times Fy given x is equals to 0 of y plus Px of 1 x is equals to 1 of y plus Px of 2 Fy given x is equals to 2 of y. So these are the things. As I know, this is 1 by 3 times now this distribution. So what is this distribution? Y given x is equals to 0 will follow
Normal 0, 0.5.
0, 0.5.
But here 0.5 is mean or the standard deviation actually?
See, this is variance.
Sorry, I mean variance or standard deviation is the question. Yeah, okay.
So always normal has 2 parameters. One is mean and another one is variance.
Okay.
So we know the density function of normal, right? So I will just write it here. Y given x is equals to 0 will follow normal 0.5. Y given x is equals to 1 will follow normal 1.5. Y given x is equals to 2 will follow normal 2, 0.5. Okay, so this will be 1 by root 2 pi. Sigma is again square root 0.5 into e to the power minus x minus 0 whole square by 2 into 0.5. Okay, this is okay. Y this will be y plus I will have 1 by 3 times. So this is again 1 by 3 times this time. This stays the same. E to the power minus, instead of y minus 0 we will have y minus 1 whole square into 0.5 plus we have also the third term which is 1 by 3 into 1 by root 2 pi root 0.5 e to the power minus, here it will change, y minus 2 whole square by 2 into 0.5. Now see, a few terms will become 1. So this is 1, this is 1, this is 1. So if I simplify it, again this root inside 2 times 0.5 will be 1. I will only have 1 by 3 root pi. So 1 by 3 I just multiplied it. E to the power minus y minus 0 whole square plus the same thing 1 by 3 root pi e to the power minus y minus 1 whole square plus 1 by 3 root pi into e power y minus 2 whole square.
So root 2 pi will be, right?
See, 2 and this root 0.5 will get cancelled, right? It will become 1. So 2 times 0.5 will be 1, right?
Okay, I didn't notice it due to clumsy calculation. Sorry.
So 1 by 3 root pi, 1 by 3 root pi, something like this we will get e to the power minus y square plus e to the power minus y minus 1 whole square plus e to the power minus y minus 2 whole square. So now you can easily observe that this is not normal anymore. Okay.
Yes.
So even though I took my conditional densities are normal, my marginal density of y may not be normal, but it is not normal, but this is called as mixture of normal. Okay, it's the collection of normals. It's not normal, but it's mixture of normals. It is like adding 2-3 normal distributions.
Excuse me, sir. Sir, here marginal density is same as joint.
No, definitely not. Marginal density is different from joint, right? How do you get the marginal density? You have to sum over all the unwanted random variables range with joint to the joint. Marginal talks about single random variable. Joint is between two random variables.
And why are we doing a marginal of x into conditional density of y?
Because then only we will get joint for the each individual case.
Yeah. So see, as we have discrete and continuous, observing from the continuous random variable will be difficult as of now. So we can't straight away start from dealing the maybe marginal of continuous and seeing the conditional density on discrete given continuous and then looking the joint is very difficult path to pick. Instead, as we have discrete in our hand, we know the PMF of discrete and we know the marginal of discrete that we can compute. So marginaling the discrete random variable and looking conditioning of y given the discrete condition of continuous given discrete also easy to see, because given discrete means I can actually pick each and every value in the range, and producting these two I will get the joint. So looking the joint from this perspective is easy than the other side. Okay, so that is why we see it from this side. So we can easily find this px, so the marginal of x, and also it is very easy to observe the continuous random variable given the discrete random variable. Okay, so vice versa will be little difficult, and in week 6 we are anyway going to do between two continuous cases. Then we will definitely have to marginalize one of it.
Sir, how do you visualize this distribution, this joint distribution?
So yeah, so that is the problem in continuous case. So there is no longer we have the tables with us. Okay, but instead what we do is we will move to the graphs slowly. So we will look the graph and visually look at the distribution on xy plane. So if
something like that can be done for this, whatever example you have taken.
Yeah, but it requires 3D graph, right? It requires me 3D graph. Where, see this, I have to draw this normal given
x.
Okay, and I also need to have x, and I also need to have fx, this fxy. So third thing. So three things are like y given x is equals to I, and the other thing is x, and above there will be some third axis which will talk about maybe fxy or fy. Okay, it will require some 3D graphs.
Yes.
Okay.
Can we represent the information partially on a 2D graph, like only the relation between xi and y?
So in 2D what happens? X is taking values 0, 1, 2. When x takes 0, my y, so this is y, y given x is equals to I. So when x is 0, how it will be? Somewhat like this.
The mean is around 0.
Mean is around 0 and it will come like this. In the third axis, you see, it will be like this shape. Okay, it is very okay. Just give me. Let me go to other page. Let's visualize. Let me properly draw the 3 axes for you. Okay, let's say this is. So I want my graphs on that side. So able to think of this as 3D, right?
Yes, sir. Thank you.
Now, let's take this as x. X is on here, 0, 1, and 2. And if you see at 0, the graph will be somewhat like this. Okay, you see on this plane, okay, this straight plane, this plane, this is your axis.
YZ.
Okay, yeah, look it on YZ, and at 1, what happens is this will follow. Okay, at 1, you have the line first. I won't change. Okay, let's say this is 1. Here the graph will be normal and the mean will be at 1. So mean will be, if I say this is y given x, if this is 1 and this is 2, the graph will be like this now. So this peak will occur at this point. Okay, slightly shifted 1 units towards right side. And at 2 it will be the same thing, but it will be at pretty hard.
Sir, which graph is it? Normal graph?
Normal. So is that bad, my drawing?
No, it's not
No,
about
sir, it is
bad,
good.
but
It is very good.
understanding it is taking some time.
Okay, so this will be like this, and this peak will occur at 2. Okay, this is how it will be. So this is normal. So this is how the graphs will.
It is getting translated by 1 unit.
1 unit to the right side, and it is shifting 1 unit to front, maybe on the x-axis. Okay.
Okay, thank you, sir.
So
Now
this
it's
is how
clear.
this is how it will be, and yeah, this will get this will be more complicated if it is between 2 continuous. See, we have graphs. Okay, we don't see it in 3D. We will see it in 2D. Then between x and y only we will talk in continuous. We don't bring this density function at all into the picture. Rather, we will just draw the graph between the support of x and support of y. That's it.
Sir, if we were to look at the YZ plane only and ignore the x-axis entirely, then we will see all the 3 distributions overlapping and shifting towards right.
Overlapping and shifted towards right side. Yeah, correct. Yeah. So if you are seeing from the x positive x direction, So your graph will look like overlapping and one unit shifted towards right.
Thank you very much, sir, for that effort.
Okay.
It is clear now.
Okay, thanks. So this is the last topic we have. We do have this conditional probability of discrete given continuous. Now, in continuous, if you know that your random variable y is taking a particular value, how will this discrete behave? What are these conditional probabilities? Discrete given continuous now. So the same setup we have, X is discrete PMF with PMF P of Px and range Dx, and we have this marginal. What is this? This is conditional. Continuous given discrete. Okay, this is continuous given discrete. Just this thing. Previously we discussed, right? This is nothing but this yx. Then the conditional probability of x given y is equals to y naught. Now this is given. Okay. This is given that my continuous random variable has taken this value. How will the probabilities affect the discrete random variable? So this is given as probability that x is equals to x given y is equals to y naught. I can write it as the joint divided by marginal. So the conditional is the joint divided by marginal, right? So the marginal for y is nothing but the PDF we have, fy of y naught. And the joint, how we can write the joint? We can write it as marginal times conditional. So we know the marginal of x, we know the conditional given conditional density of y given x. So we can write that joint as px of x times fy of x, fy given x is equals to x of y naught.
Here we write joint in two ways, right? That's all.
Yeah, correct.
And then find
Sir,
whichever you want.
sorry, a doubt. So isn't y a continuous variable?
Yeah, it is continuous.
Then how can it take at a particular point? Probability.
It is given. See, even though it is continuous, if you randomly generate a value, it will give you some value, right? Even
But sir, f denotes a probability, right?
No. So that is why I use these notations. P and F. F is densities, density functions. P is the probability mass function.
Sir, but density does not occur at a point, right? Like it occurs in an interval, right?
No, see, we shrink that interval, right? So while we did in week 4, we have shrunken that interval to at a straight point, right? Straight line. So that is what density, right? Density at that point, right?
Okay.
So that is why we call it as density, right?
Sir, PDF is density around the point, sir.
PDF is density around that point, and that around is very, very, very small. Very, very small.
Okay, sir.
Okay, so we have this density function, right? Fx of x. What will this give me? At a point x, right? At point x only, it gives me the density.
Okay.
Sir, is this next concept or just joint only?
No, this is which one?
Conditional probability. This is next.
This is the other some subpart thing. So we can also compute conditional probability discrete given continuous is what we are discussing. Okay. So if we solve the problem, I think we will. This is the last problem I have. Before that, if x and y are independent, again we have to look these cases also. So as x is discrete and y is continuous, what happens if x and y are independent? So the conditional will become marginal. So this fy given x is equals to x of y is no longer dependent on x. So it's simply the marginal of y. And this conditional discrete given continuous will simply be the PMF of x, again the marginal. So conditional probabilities or the densities will become the marginal densities and the marginal probabilities, PMFs. Okay, this is for continuous, which is y, and this is for discrete, which is x. Okay, conditional will become marginal for y if x and y are independent. Conditional will become the marginal PMF for x. Okay, the same thing will happen here also. So this is the example I have, final example. If we solve this, I think I hope week 5 is lot more covered. Okay, so I have x is uniform between -1 and 1, and I also have conditional density of y given x is equals to -1 and 1. So this is like y given x is equals to -1 is one thing, and y given x is equals to 1 is another thing. So when y given x is equals to -1, so this will follow uniform -2 to 2, and when y given x is equals to 1, this will follow exponential 5, exponential distribution 5. What I wanted is probability that you have to find probability that x is equals to x I have given. So x means you have to find when x takes value -1 and when x takes value +1. Yeah.
Sir, I have a small doubt. So x is uniform between -1 and 1, and y given x equals to -1 is uniform between -2 and 2. But in both cases, you have used one curly bracket and the other one is third bracket. So what is the difference between these two brackets?
See, there is no much difference. So the parameter is represented in open brackets. The intervals usually we will represent, if I want to include -2 and +2 into the interval, we will give it in the square brackets, or else we will give it in the open brackets.
That one is understood, sir. But for the initial x is uniform between -1 and 1.
Acha, that one. Okay.
Yes.
So usually this square bracket and this open brackets we will use for continuous random variables. Okay.
Okay.
And this thing represents the set representation. Set is represented in third brackets or the curly brackets.
So it's a x is continuous and
x is no. This is for discrete. This is continuous.
Okay. Yeah.
Okay. So this is set means, so within this it has value. Whatever the elements
only
present
that
in the set, only that x can take. And this square bracket and open bracket represents the intervals or the parameters like this. Okay. Only the confusion will come only in the uniform case. Okay. So when we give this square brackets and open brackets, then it represents for a continuous uniform.
Okay, sir. Okay. Yeah. Thank you, sir.
Yeah. Okay. So what is this? So okay, we are out of time. So this thing I want. So for the first part is like when x takes -1 and when x takes +1. So one thing is, one of this is very easy. Which one is that?
So the -1 is easy because exponent 5 will only take positive values.
Exponential 5 will only take positive values.
So that means that if y equals -1, then that means x has to be -1.
Right. Right. That's the best answer. We can, instead of computing all the things, you simply see it is given that y has taken value -1. Now if y has taken value -1, now we are in the world of y has taken value -1. And what are the possible cases where y can take -1?
Uniform.
Only in this case, right? In this case, it is not possible that y can take value -1. So this case can be ruled out. And if you observe, if y, so only this case is possible. And this case is nothing but, this is in the world of x is taking value -1. So if y is taking -1 means my x has taken value -1, and this y given x is equals to -1 case, we gone into this case, and then y can take value -1. Then only y can take value -1. So that is how you have to observe. And even if you compute, you will get
Answer is
1 and 0. Huh?
So answer is 1.
Right. So when y is -1, when y is taking value -1, definitely my x should take value -1.
Sir, sorry, but I didn't understand.
You didn't understand. Okay.
It is pretty roller coaster type of thing.
Okay. So will you agree that okay, let me put it in this way then. Will you agree with this?
Yes, correct.
Is this true? See, for any y given, x can only take two possible values, either -1 or +1.
Correct.
Correct? Okay. So that means the sum of these two probabilities should be equal to 1. Correct?
Yes.
Now, so look at these cases. Y is equals to -1 means, when can y take -1? This is what you have to see. So if you go back, when x is equals to 1, y follows exponential distribution.
Yes.
Right? So there is no when x is equals to 1, there is no possibility that y takes value -1.
Okay. Because
right?
exponential is positive always.
Exponential is the support of exponential distribution is greater than 0. So from there, what you can observe is x is equals to 1 is not a possible case. If x is 1, then y cannot take -1. But what we have given you, y has taken value -1.
Yes.
Right? So if y has taken value -1, then x didn't take value 1.
Yeah, there is a contradiction.
Right? Yeah. So that means x taking value 1, given y taking value -1, this will be 0. So x will not take value 1. Or you see it in the other way. If x has taken value 1, y will not take value -1.
Yeah, no, understood.
Okay. Yeah. So if this is 0, this will be 1. So that means if y is -1, then definitely x has to take -1.
Sir, actually, I have a problem of understanding this, because this y equal to -1, it should be a continuous random variable, right? So
Continuous random variable, right?
so how it can get a value at a particular point, like y equal to -1? That's what
How it can get is, see, this is we are giving you, okay? So if I say y is, okay, let's say y is uniform between 0, 1, okay? What this means, y can take any value, can take, right? It can take any value between 0 and 1. So y can take 0.2, y can take 0, y can take 0.5, y can take 0.7. All these values y can take actually, right?
Yeah.
But probability that y takes those values are 0. Okay. So if I randomly generate some value for y, so for some one instance, okay, so I will get, right, I will get a value, right? If I randomly generate value between uniform 0, 1, if it has given me 0.2, okay, so that is what we says. I have randomly generated my y and it has given me that value as -1. So now given y is -1, so we are in that world. Okay, we are no longer in the continuous complete thing, but in one instance, I know that my y has taken this value. Then what is happening to the discrete random variable are the probabilities? What are happening to the probabilities of the discrete? Okay, so continuous cases, y can take any value, but the probability that y takes a particular value is 0.
PDF is 0, sir, at a particular point.
PDF is not 0.
The probability of this.
Probability is different from probability density function. Okay, see, y takes value is possible. So treat it, y takes a value is possible, definitely possible.
Yeah, that's correct.
That's correct.
The
Probability, probability that y takes, okay, y takes a value small y is possible. Probability that y takes a value, y takes value y is 0. So this is 0. Probability is 0.
Okay.
It doesn't imply that y will not take that value. Y can take that value.
So the earlier one, how can it be 1? It should be 0, right?
Which one?
Like the addition of that probability. Yeah, this one.
This one.
Oh.
This one is like, see, given that y is 1, even though if it is not given, okay, so that is just the condition we gave. Probability that x is equals to -1 plus probability that x is equals to 1 should be equal to 1.
Yeah, because only 2 conditions are
there are only 2 possible values. And the condition given is some other random variable, one random variable is taking value -1. So even though this condition is given, the values that x takes is between -1 and +1.
Yeah, that's correct.
That's correct. So if I add these probabilities also, it should give me 1.
Okay.
Right? Yeah. Now within these two, one is possible and one is not possible at all. So the probability of the other is getting 0. So that you have to observe why it is getting 0.
So if it's not getting 0, one term is not getting 0, so
that we have, right? That we have this. If we compute this, then we can. So even this is not. So I'm not saying that this is the only approach. So this is the best approach. This is how you have to think.
Okay.
But if you use the formulas and everything what we discussed till now, eventually you will reach. You will get 1 for this and 0 for the other. Okay. So the formula thing we are going to use for the second case. Okay. Now I want probability that x takes value -1 given. Now my y has taken value 1, and also I want this. What are these? So use the above formula we have. So what we have? So we have px of -1
joined by marginal.
Joined by marginal, and that joint I will write again it as marginal times condition. If y given x is equals to -1 of 1 divided by fy of 1. So you see in this case why I am saying, see even this if you write, what will this happen? Px of 1 times fy given x is equals to 1 of -1. So this is this thing you observe here, when x is equals to 1, probability density of y at -1 is 0, because y given x is equals to 1 is exponentially distributed and it cannot have some density at -1. So this will go to 0. So if you use the formula from there, so use the formula and you can get it. Okay.
Actually, this is the marginal for y, right? The p of x into. P of X. It's
P
one.
of X into, this is joined. See, this is conditional.
Conditional into marginal, yeah.
So conditional can be written as joined by marginal.
Mm-hmm.
And this joint, I am writing it as marginal times conditional.
Okay.
So like this. And the other one is Px of 1 times Fy given X is equals to 1 of 1 divided by Fy of 1. So these are the things. So I have this. I have this also. Right? Because I know the distribution of y given x is equals to -1 and y given x is equals to 1. And I simply need Fy of 1. So for Fy of 1, I need the marginal density of y. For that, we use this thing. So marginal density of y, we will just find by summing over all the values of x that are in the range Px of x times Fy of x. So you can try it out, I guess, as we are very much short. It's already 20 minutes done.
So can you show the question, please? I will take a print screen.
Okay. So anyway, I will upload it right after this session.
Okay, sir.
Okay.
Sir, sir, for a continuous random variable, probability at a particular point is 0 and PDF is not 0.
PDF is not 0. PDF is not 0 in support of the text, and PDF will be 0 outside of the support. This one is very easy again. So what will be the probability that x is equals to -1 given y is equals to 5, and what probability that x is equals to 1 given y is equals to 5? So what are these values?
So similar to the first case.
Yes, sir, similar.
So now y is given that it has taken value 5.
First will be 0, I guess.
Exponential only, sir.
Only possible case is exponential case. See, when y is 5, it cannot be from this distribution. Of course, it is uniform between -2 to 2 only. Okay. So that means x cannot take -1. Again, the same thing. So this will be 0 and this will be 0. Okay. Using the formula, you just get these values. And I think maybe I will just leave it as an exercise, and maybe in the next class we can, if you want solutions, we can discuss. Okay. And this is about week 5. And I strongly recommend everyone to solve each and every problem which you see on the portal in the internet. So you just open the internet, go to internet and just type some problems on discrete continuous, some problems on CDF, PDF of continuous random variables. So please do that. If you do this, then your life will definitely be easy after week 7. And if you are not doing all these things, then definitely life will become much more harder in coming weeks. Okay, it's all depends on you.
So coming terms also.
Definitely coming terms also. As this is foundational course, if you should pay attention for each and everything. Okay.
Sir, I have a small doubt on week 5.1 activity question number 3. So I have approached it. So if you can open it, I'll say.
Okay, let me open that.
Yeah.
So I'm just stopping this this thing, and I will just share the.
Sir, will you upload this after the class?
Just after the session I will upload. Okay.
Okay. Where is it generally uploaded?
It will upload in the live sessions 2023, live session notes 2023, under the tab of live sessions. So you will be having the live sessions of the previous terms. And below that, there will be separate tab called live session notes, Jan 2023.
I guess the portal is
But today, tonight, 10 to 5, the dashboard won't be available, I believe. There's a
Yes, it is under
Even
maintenance.
if you upload, we would be able to see it tomorrow morning only.
Night 10 to 5.
10 to 5, yeah.
Okay.
Yeah,
So
5 till
then
5
yeah.
a.m. But it usually takes even later, right? Maybe 5, maybe 7 a.m.
Okay. Maybe I will try to upload. Maybe backend also might be people rigorously working on it. I don't know if I can upload. If I can upload, I will straight away upload it.
Also not
It's a global fix for some issues which were happening, right?
Okay. So yeah, so 5.1.
Question number 3 and 4.
Oh, it's not opening.
Okay, sir, I'll say.
Just
Sir, I think it is for you as well. Means everyone is.
So everyone is.
No, it's not visible.
So the question is x is uniform between -3 and 2.
Okay, let me write it down. Oh, let me share back my journal screen again. Where is this? This is AQ. 5.1.
3.
Question
3. Question number 3.
3.
Yeah.
Okay, just tell me the question now.
X is uniform between -3 and 2.
X is uniform, continuous, right?
Yes.
-3 and 2.
Right.
Closed?
Yes, both are closed. Then what is the distribution CDF and PDF both for mod X?
The CDF and PDF of mod X.
Right.
The question is CDF of mod X.
Yeah. Question 3 is for CDF and question number 4 is for PDF.
Okay. So this will more or less give more insights for -3 to 1, which we did yesterday.
Right. Correct. So for y between 0 and 2, it will be from -x to plus x.
Let me draw the graph. For me, it will be easy if I draw the graph. Okay, so that is why I'm drawing the graph. So it will be mod x. So till 2 only. Okay. So I think this is -3 and this is 2. So what I want to find is PDF of x, CDF of x. First we will find the CDF, then we can get the PDF. So I want fx of x, and this small x. Okay, you observe this small x starts from -3 to 2.
Yes.
Okay, so I have to go from -3 till 2. Fine.
Yes.
So now how will I find? This is standard thing, probability that, sorry, fy of y, right?
Fy. Yeah.
Sorry, and this starts from 0 to 3. Right?
Yes.
Or maybe what will be the support of y? What will be the support of y? As y is mod x and x is uniform between -3 to 2.
0 to 3.
0 to 3. Support of y is 0 to 3. Okay. And this y, the small y, should take all the values from 0 to 3. Okay. And below 0, first thing what I know is base things are when y is less than 0, my CDF is 0. When y is greater than 3, my CDF is 1. This is okay. Yeah. And I need to find the intermediate one. So 0 less than y less than 3. I don't know whether I will get it in one shot or do I have to split that interval also into some 1 or 2?
Yes, sir. We have to split it.
We have to split it.
0 to 2 and then 2 to 3.
Yeah, 0 to 2 and 2 to 3. So y less than, so this is the basic definition I have for CDF, which is this, and this is probability that mod x instead of y I can write it as mod x less than or equals to y. Okay.
Yes.
So now you see my y start taking values from 0. So this is 0. So this is y, right? This is y. So now you see, you have to see in this perspective. So you just rotate or whatever convenient method you have, you just do that. Y and x, how will my graph be? This is how the graph. Right? Now my y starts from here and I have to go till 3. Right?
Yes.
Now this fy of y is basically if there is any y in between, I have to compute the area under this. Right?
Yes.
Till.
Yes.
Right? That is how you should observe. So till 2, I have a area. I have a bottom line. Okay. Bottom bound also I have. But after 2, I don't have a bound. Okay. So I didn't have any bound, but just take it like this. Okay, it's constant. After 2 also it's 2 only. Okay. Or okay, let's forget about that. Just come here. Okay. So I want to find my CDF of y till 2. Let's compute till 2. Okay. Let's see after 2 it is something we don't know. Just for time being, just remove the 2 to 3 case. Till 2 I can compute, right? Till 2, when y is till 2, what happens? So this will go from, so what are the limits of y? I have
minus x to x, I think.
Minus y to, okay. So this is like minus y to y.
Right.
Okay. Or x, or else if you are seeing in this graph, it will be like my y will take values between minus x to plus x. So this is okay, minus y to y. I just wanted to write it in x terms only. Okay. So I'm just drawing that the same thing here. So any y below 2. Okay, this is the 2 line. Y is equals to 2 line is this. Any y, any small y below 2 and above 0 will cut here, right? And the limits of x will be, so if this is y, this is minus y and this is plus y. Okay.
Okay.
So now this will become fx of y minus fx of minus 1. Right?
Yes, sir.
Now, what will be fx of x?
1 by 5.
No, that is density.
Okay, x by.
This is 0 when x is less than minus 3. X by 5 when it is between minus 3, x to 2. When x greater than or equals to 2, it is 1. Right?
Yes.
Now you see here my y, my x, this is y and this is minus y. Okay.
Yes.
and this y and minus y will lie in this interval.
Yes, yes.
Right?
No, not which interval, sir?
This one. See, okay, fx of y. What is fx of y? This is 0. Instead of x, just substitute y. Y by 5.
Right.
When y is less than minus 3, when y is in between minus 3 to 2, 1, when x is greater than or equal to 2. Right? What will happen to minus y? Fx of minus y. So this will be 0 when minus y is less than or equals to minus 3. Right? Instead of x, just substitute minus y.
Okay, minus y by 5.
Minus y by 5 when it is between minus 3 less than or equals to minus 5 less than
2. Yes.
And minus y greater than or equals to 2. So this, if you simplify, what you are going to get is when y is greater than or equals to 3, I am going to get 0.
Yes.
Okay. So that will invert the things. Okay. And we have to take the intersection. So we are at x only. We are in x. So understand it. Okay. Let's do it in this way. Okay. So you know this y is anyway in between 0 to 2, right? If y is in between 0 to 2, where will my x be?
Minus 2 to 2.
Minus 2 to 2. Agreed? And this minus 2 to 2 will lie in this interval.
Yes.
The second one, right?
Yes.
So that means my CDF will take these values only.
Right.
If it is y, that will be y by 5. If it is minus y, that will be minus y by 5.
Right.
So that is y by 5 minus y.
Minus 2y by 5.
So this you are going to get 2y by 5. Okay.
Yes.
So the other part is when y is greater than 2.
Right.
Right. So my fy of y will be probability that y is less than or equals to y. So remember this y is greater than 2 now. Okay. So
yes.
It is like this now. Okay. So here now my y is greater than 2 and till 3. Okay. My y is in this region now. Now in this region we came. So when y is in between 2 to 3. Okay. So what happens to my probability? So I have to get the probability that y is less than or equals to y. So all the probabilities that is less than or equals to that's y. So that means if my y is here, somewhere here, okay, I'll take another color. Y is somewhere here, the small y is somewhere here. I need to get the probabilities of this
plus this
as well as this.
Yes.
Okay. So the thing is, in order to get this, I need to have probability that, so whatever the above I had, so this 2y by 5, not this. Okay, whatever the thing I had, let's split it. Okay, probability that y is in between 0 to 2 as well as probability that 2 less than y less than or equals to the small y. Can I write it like this? Right?
Yes, sir.
Now my so what is this probability? Probability that y is in between 0 to 2. When will y be between 0 to 2?
That we have already calculated 2y by 5. Yes.
When x is in between minus 2 to 2.
Yes.
Right?
Yes.
So when will x be between minus 2 to, what is the probability that x is in minus 2 to 2? This is like fx of 2 minus fx of minus 2.
Yes.
So this is like fx of 2 is 2 by 5 minus of minus 2 by 5. Both will lie in the middle interval only.
Mm. Okay, now we are taking the value. Okay, yes, yes, yes.
Now we are
Mhm.
considering whole.
Yes, yes.
There is no small y here at all.
Understood. Yes.
Okay. So we will get a constant value which is 4 by 5.
Right.
This is 4 by 5 plus I need to compute this. Okay. So when will what is the probability that y is in between 2 to the y, the small y, which is between 2 to 3. Okay, what will happen? So if I just have to write it like 2 less than mod x less than or equals to y. Okay, instead of y I just wrote it mod x. Now in which interval this will be?
-3.
0.
-3 to
0.
0.
2. -2.
-2. Right?
Right.
Only this. Only this interval.
Yes.
And I don't need to go till 3. I just need till y.
Yes.
Okay. So that means this will become y. Minus y to -2.
Correct.
So this will become fx of -2. What am I getting? Yeah, fx of -2 minus fx of -1. Right?
Yes.
So what will I get? 4 by 5 plus fx of -2 and minus fx of -y is
-y by 5.
minus y by 5. So this is again, so you see this and this will get cancelled actually, fx of -2 and this fx of -2, and we will be left with 2 by 5 only. No need of this thing. 2 by 5 minus y by 2, and we are going to get 2 plus y by 5.
Yes, sir. Sir, just one more request, sir. Can you please go above and that graph that you have drawn? Yeah, the first one. So, what is the area here? Like, it is
See, this is not between fy of y and density of density function of y and y. This is between x and y only. So there is no area under the curve computations and everything here.
Okay.
See, area under the curve comes when the graph is between density function and the random variable. These graphs are between random variables.
Yes. Okay.
And you see here, ultimately what we got, fx of 2 minus fx of -y. Right? All these things cut down to this. Yes or no? So this thing got cancelled, and we had fx of 2 here, and we had minus fx of -y. And this in probabilities, how I can write this? I can write as
yes.
Right?
Yes.
So in the case of y being in between 3 to 2, I will not take the probability that from -y to +y, rather I will take till 2 only.
Correct.
Okay, so from this you can get that, and this maybe this answers the above problem also we have. So that thing, the problem. So maybe how many people left this? Okay, 18 people, whoever are there in the session. Yesterday also we are discussing the same kind of problem. and I was trying to give you some 2-3 sides of it, and there also in some case we restricted the upper bound to 1 and we didn't go till root y.
Yes.
You can observe why we cut down to 1. So this is how you have to look. If you split the probabilities and if you compute, so you will eventually reach to this point, and this point is nothing but this, and there also we will get the same thing. Okay, so the compute so this will be like this. So finally what we got is this is what you can get. It's fy of y. Shit, I thought I should finish the session by 10 today, but it went 10:45.
Sir, we can
This is
also
the-
integrate the PDF. Right?
But how do we know the PDF? PDF is not given, right?
No, sir.
So less than y less than 2 is another thing. And the final thing what we got is 2 plus y by 5 when it is
2 to 3.
2 to 3. And y greater than or equals to 3, it will be 1.
1.
Okay. Okay. So instead of doing all these things, yesterday I told that this will, when it is in this interval, this is nothing but probability that it will take from minus y to 2, because again the graph, I just showed the graph. So if this is y, it will not go till plus y, rather it cut down to plus 2. So this is the upper bound we have. We don't have graph after 2. So I was trying to bound the upper bound to 2 only. So this might give you some more insights why we are upper bounding to 2. Okay, from this you can get the PDF, I guess. You just differentiate it.
Yes, sir. Yeah.
Okay. Yeah. Okay then. So this summarizes week 5. And
Yeah. Thank you, sir. Yeah. Thank you.
I hope now you can able to solve all the problems in week 5, as well as you can start working on week 6, because week 6 deadline is all Friday, on Wednesday. So please start looking at the contents of week 6 as soon as you finish week 5. And yeah, so we will meet next week.
Thank you, sir. Good night.
Yeah, thanks.